In this video, we're going to talk about a couple of implementation level details for a couple of operations in your binary search.java class. So you have that in your module. So please have a look at binary search tree.java for more information. In the next couple of slides, we're going to look at a couple of operations. These are contains, get, and then the iterator parts. The add remove part is something that we can talk about later. For both contains and get, these are very similar operations that takes a target, right? So the target that you're looking for inside a tree, or getting the target that you're looking for inside a tree. If there's nothing, if you can't find your target, it returns null, right? Contains, on the other hand, returns either true or false, whether this tree has a target there or not, right? So let's quickly look at these operations and quickly also discuss some of the efficiencies that we see in these operations. So the first one is contains operation. So this is a search, basically a search going through your entire tree. Now this could be, now in the context of the binary search trees, right? We know that the order of nodes, it is important because they follow a specific properties, right? The size of the value, right? Either it falls on the left or the right of a inner node. Depends on the values this node has. So a contains is a wrapper function that we will kick off that essentially talks to what we call recursive contains. So contains, right, calls the recursive contain. So recursive contain is recursive call. This is the one that is going to be recursing throughout until we're done, right? But because recall a tree can go either left or right, right? So this recurse contains recurse in this direction, left, and also in this direction, right? So as you can see, we're going to do left first and then right. But if the node is null, returns false. So contain returns a Boolean, right? So that is kind of the base conditions here. Number one, base condition. Number two is if node contains a target, then returns true, right? So either you're at the end of the recursion, that your node is null, meaning you're terminating at the leaf, right? Let's say this is a leaf. There's nothing more, so it terminates it. Returns false, right? This allows your recursion to flow back up, right? Bottom up. Then, or if the node that you're looking at that terminates as a leaf inside that sub branch is the actual target that you're looking for, return true, right? So this is it. And on a high level, we will recurse into the left as well as the right subtree. So let's look at the code, which is pretty straightforward. Your wrapper function, which method is the contains, right? This returns a Boolean. This wraps a recursive call, right? Starting with root, okay? And because you're going to be recursing this this call throughout, we're not going to call it root. We're going to call it node here. So node is of type BST node. So this is also in your modules. Take a look at the constructions and see if you can without looking at this BST node, you can pretty much write out the function without memorializing this thing. So rec contains has a couple of selection criteria. So the first criteria is if the null is null, right, return false, because there's nothing to look at. So at this point, it recurs, right? The bubble goes up, right, back into the calling function. So 3 selection criteria, actually 4, right? The first one is the edge case, right? So we established that, and then the other 3 here is the result of a compare. So first of all, you got to make sure that your target and your get info, this is of type that could be that is comparable, right? So you want to make sure that you have provisions out there that compare these things. If this is a string, then yes, you can invoke its own compare and do a comparisons that way. But recall a compare is different than equal, right? Equals returns Boolean, true or false. However, compare gives you either positive, negative, or 0. So these are the 3 scenarios. 1 is when the result is less than, is a negative. 2 is the result is positive. The third is they're equal, right? So if this is equal, returns true because you found it, right? But if not, if this is 1 or 2, then you want to further recurse into its deep end. So If this is larger, then you know you can keep going into the right tree, because we know when a value is greater than 0, that means your target is actually greater than your get info. So in this case, the target's got to be on the right subtree, right? So you got to recurse into the right one. However, if the target is less than, right, get left, in this case, you get negative, right, number. In this case, you know the target, given the binary search tree property, that the target has to be on the left subtree, right? So you further recurse into it as a result. So this reestablishes your top to bottom recursion, top down recursion until you find it. If not, then eventually when you get to the end, you don't find anything, you return false, and that's gonna just basically, recurse everything back up again. This will work when your tree is not really, it's not too deep, okay? Otherwise, you're gonna run into danger of running out of memory doing stuff like this. Anyway, so that's contain, and your get is just like your contain, right? It has a recursion, and this recursion get allows you to kind of recurse into either left or right, depends on the property of your value, your get info, right? So for selection criteria, again, these three are a part of your compare, either positive, either negative, or they're equal, right? In this case, returns. So when this is equal, meaning you found the target, you want to return that node's get info, or you can return the target itself, doesn't really matter. As long as this is type T all the way back up, and then you're done. If not, then just keep going left and right. And the reason why you can do that is because of the binary tree properties. You know exactly which part to look for. Now, a question is, what is the efficiency of this? Right? As you can see here, the recursion kind of goes into both left and right, in the order. Now, it is very possible that in a binary search tree, since this binary search tree could be looking at this, right? It is okay, right? As long as the tree, has both left and right null. So each node, in this case, the right node turned out to be null, right? But it doesn't mean that it does not have it. It's just that the tree looks like this, but this is still a binary search tree, okay? As long as the value kind of matches. Now, this is the worst case scenario. If you had to go all the way in a singular direction like this, there is no sort of, when you get here, the values here in this direction, and then you can keep recursing on this directions and so on and so forth. The worst case is you're gonna have to visit every single one of these nodes, right? And this applies to get and contain as well, right? So worst case means big O. So the worst case scenario for get and contain, in general, searching a binary search tree is O of n, right? So this is not very enticing, right? But what is really going to be useful is thinking in terms of a BST, having a balanced structure. So if you have a balanced tree, meaning this tree is exactly, divided into this sort of left and right, right? So meaning each right node or left node has a corresponding left. So this allows you to, right? So if you build something like this, so it looks rather balanced, right? There is a right, there's a left, there's a right, there's left. And this allows you to, right? So you can keep on going and establish your balance tree. Now, if you have a balance tree, then the time complexities in getting a get and search, in this case, would be O of log n, okay? Why? Well, because you can, right, at any step of the way, you can pretty much just eliminate. Let's say if this is the direction, let me use a different color. Let's say if this is the direction that you're heading, right? You can effectively, let's say if you go this way, you can get rid of the other half, right? And the reason why I can say the other half is because this is the balance tree, right? So in a balance tree situations, O of log n, but if the tree is not balanced, but it's a search tree, then the efficiency for get and contain is O of n.